Well, it's time to the last talk of today. Let me introduce, thank you. This is for close. Our next speaker is Mike Renier. I say in close to French, sorry. Are you there?
Yes.
Yes?
Yes,
And
I'm here.
Mike will talk us about history and philosophy of chemical modeling. Welcome, Mike. All
Thank you.
yours.
Okay, good. Um,
Is this the second one?
yes.
Yes.
Interdisciplinary chemical modeling involves advanced algebra, computer science languages, Fortran, Python, C++, and physical chemistry concepts like chirality, non-covalent and covalent bonding, and Boltzmann distributions. And also, it's a great idea to do benchmarking with experiments like X-ray crystallography, which can calculate molecular electrostatic potentials. Next slide, please.
Yes.
Quantum mechanics really started back in the 1920s with Professor Schrodinger work on the wave function. And he did say that the wave function is a mathematical construct, not a function in real space. And later on, Professor Bader said it's not to be used to interpret physical observations. Next slide, please. In quantum chemistry, there's a relationship between the number of orbitals and the speed of the calculations. Hartree-Fock and density functional methods scale to the power of 4, and they're much faster than Moeller-Poiseuille, couple cluster, and configuration interaction methods, although these methods have higher accuracy than Hartree-Fock and density functional. And there's a good book in Reviews in Computational Chemistry about this quantum chemistry scaling. Next slide, please. Molecular mechanics was started in 1968 and 1969, and was part of the Nobel Prize in Chemistry with Michael Levitt and Ariel Warshel. They looked at small molecules and proteins, and I questioned whether the terms are really additive. There was 5 terms that were additive, and whether they're actually additive is a good idea or not. One good thing about their work is that they benchmarked their theoretical calculations with experiments, and they had a statistical term. The shortcoming of the work was there wasn't a solvent term involved. And benchmarking with experiments was published in Angu Chemistry International Edition in 2017. And I feel it's a good idea to benchmark theoretical calculations with experiments like X-ray crystallography. Next slide, please. The HELLMAN-FEYMAN theorem is about the coulombic forces exerted upon nuclei. The total energies are expressed by electrostatic potentials, and there's an electrostatic and polarization component. It also looks at dispersion forces around nuclei. Both the energy and forces are complementary in nature, and this was published by Professor Peter Pulitzer in 2018. Next slide, please. Molecular electrostatic potentials, the importance of that is that it's a physical reality, and sometimes that's the most important thing in theoretical chemistry, is to look at the physical reality and compare that to X-ray experiments. With Professor Pulitzer's work, he was looking at sigma and pi hole bonds. Primarily, he was looking at non-covalent bonding with hydrogen and halogen bonding. And future work will be looking at covalent bonds, which are both electrostatic and polarization in nature. The limitations of the work and kind of the lack of velocities it's always been done in the gaseous state, and it hasn't been done in the solvent state. And he's always comparing his calculations to internal standards. Next slide, please. Monte Carlo simulations is becoming more popular in recent years because there's dynamic situations in the field of chemistry. like in drug discovery, there's Monte Carlo and molecular dynamics, because you're looking at the ligand interactions with the drug receptors. And Monte Carlo looks at the volume and temperature of the particles, and it chooses a configuration with the Boltzmann probability, and it weights the configurations evenly. The only limitation of the Monte Carlo model is that it doesn't represent the variables very well. Next slide, please.
Well, sorry. Oh.
Molecular dynamics is based upon the harmonic oscillator model. And typically, molecular dynamics has been used to look at implicit solvent situations, a continuum solvent condition. Recent times have looked at the conductor-like screening model, which looks at the dielectric constant of the solvent and the medium. And these calculations have much better accuracy, and they can actually look at the charge distribution on the solvent and the solute. The only limitation with molecular dynamics is the equation of motions over longer times, like in protein folding simulations, is limitation. Stochastic dynamics, Lagrangian dynamics can look at a viscous solvent situation, but not implicit solvent. And Brownian dynamics can look at random walk simulations with solvents. The current limitation of molecular dynamics methods is that it doesn't look at an explicit solvent where you sort of place the solvent molecules around the solute. A good book to look at for computational chemistry methods and approaches is Professor Christopher Kramer's book, Essentials in Computational Chemistry. Next slide, please. One situation that happens in drug discovery between a ligand, a drug ligand, and a protein is a buried cavity scenario. And some of the current approaches are integrating molecular dynamics and Monte Carlo methods to look at the Boltzmann distribution of states. And the second method is a method to look at using statistical mechanics, molecular dynamics, and quantum mechanics, where you can actually calculate the energy of interaction with quantum mechanics. And there's two references there that describe the solvent distribution and analysis methods that happen in drug discovery with drug-like ligands and proteins.
Next.
That's my final slide. Next slide, please. And I'd like to acknowledge my family members, Tom and Karen, for their financial assistance for this project. Thank you.
Thank you. Thank you very much. Questions? I will, please.
There is one of Marina, no?
Marina. Yes.
Yes, in the chat.
Yes.
Yes.
Thank you, Mr. Renier, for your presentation. I just wanted to clarify something you said. When you're talking about the Monte Carlo simulations, in terms of them being used most recently, you're specifically referring to molecular dynamics, right? Not to science in general.
Yeah, I'm kind of referring to molecular dynamics. Yeah, that's kind of the current trends to go towards molecular dynamics. So
okay, yeah, because they've been used in particle physics since the mid-70s, so that's why I wanted to clarify that you were specifically referring to that. Yeah.
Yeah, drug discovery applications. There's more recently molecular dynamics going towards that.
Okay. Thank you.
Anyone? Another questions?
I wrote the question in a queue in the chat.
In the chat, yes.
Yes. Can I ask?
Without answer.
Can I ask?
Yes.
So now, Mike, in one moment you linked X-ray experiments with physical reality, like physical reality emerged when X-ray experiments were performed. I want to know, what do you mean with this link between physical reality and X-ray experiments?
Well, I'm talking more about the electron distribution around molecules, and that being sort of the physical reality situation, and looking at the electrostatics and polarization components from a theoretical standpoint, and comparing that to the electron distribution from X-ray experiments. So,
okay, thank you.
yes,
Thank you.
you're welcome.
Anything else? Well, if we don't have any other question.
Sorry, I think that
I have a question, if I may.
Yes.
Yes.
If you were to summarize your talk in 2 or 3 sentences, Mike, what would it be?
I think the importance of chemical interactions in drug discovery is becoming very crucial for the field moving forward. And I think that's my main point. And that's kind of what I wanted to talk about, the physical reality situation between X-ray experiments and theoretical calculations. So.
Okay, thank you.
Okay.
Thank you.